Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss Bose-Einstein's statistics. Let's begin. Identical particles are classified as distinguishable or indistinguishable. Identical particles with distinguishable are considered as in classical statistics and they follow Maxwell-Boltzmann statistics. Similarly, identical particles with indistinguishable are under quantum statistics and they are further classified as bosons and fermions. Bosons particles are satisfy Bose-Einstein statistics. In the same way, fermions satisfy Fermi-Dirac statistics. Here we discuss Bose-Einstein's statistics. We have to consider a thermodynamic system. Let us consider a system and that particular system consists of n number of identical indistinguishable particles and these particles obeying Bose-Einstein statistics means these particles are called bosons. Some property of bosons, as we know, the bosons have zero or integral spins. Some example of bosons like photons, pi mesons, kaons and eta mesons, these are the particles that are under bosons and these boson particles do not obey Pauli exclusion principle. What exactly Pauli exclusion principle indicates? According to Pauli exclusion principle, two identical particles do not occupy the same energy level. Means in a particular energy level we can't situate two or more number of identical particles. But in case of bosons, as bosons do not obey Pauli exclusion principle, we can say in a particular energy level there are multiple number of atoms. Now statistically we can show how energy is distributed among these particles. These particles are bosons. Let that system is divided into k number of compartments. Let n1, n2, n3, ni up to nk be the particles having mean energies u1, u2, u3, ui up to uk respectively in the compartments numbered as 1, 2, 3, I up to k, and each compartments further divided into a large number of elementary cells having equal size as gi, g2, g3 up to gk corresponding to that of compartments. Let that entire system divided k number of compartments. That is compartment 1, compartment 2, compartment 3 up to let compartment I, and here is compartment k. In that of compartment 1 it has number of particles n1, compartment 2 number of particles n2, and compartment 3 it will be number of particles n3. Similarly, at ith compartment number of particles ni, nk, and the mean energies means the particles present in that of compartment 1, n1 number of particles, and these n1 number of particles having mean energies u1, it has mean energies u2, u3, ui, uk. Again, these compartments are further divided into a large number of elementary cells, and these elementary cells are in equal size. Let compartment 1 having number of particles n1 and the mean energy is u1 is the number of elementary cells g1. Similarly, it will be g2, g3, gi, and gk. For ith compartment, number of particles ni having the mean energy ui, and it is further divided into large number of elementary cells, and the number of elementary cells are gi. So, the thermodynamic probability, therefore, the thermodynamic probability of the system is thermodynamic probability of the system is given by, that is W with the thermodynamic probability. Thermodynamic probability is the possible number of macrostate in that of particular system. Here we are considering the bosons, and bosons do not obey Pauli exclusion principle, and the characteristic of these particles are identical and indistinguishable. Let we consider ith compartment. ith compartment. For ith compartment, it is divided into gi number of elementary cells and total number of particles here is ni. That for ith compartment. Okay. Look here how these particles are arranged, means what be the number of meaningful arrangements. Look here, since it is gi number of compartments, so it has gi minus 1 number of objects for gi number of compartments. It has gi minus 1 objects since the particles are indistinguishable, so this is the Ni number of particles with Gi minus 1 number of objects. So the total number of objects will be Ni plus Gi minus 1. Here the total number of objects is equal to Ni plus Gi minus 1, and this total number of objects are arranged as there are exactly Ni number of particles are arranged, which is the meaningful arrangement. So Ni plus Gi minus 1 number of objects are arranged in Ni number of ways. Therefore, to calculating the thermodynamic probability of the system, for ith compartment, and then we use the multiplier from I from 1 to k, that will be the thermodynamic probability of that given system. So what be the number of meaningful arrangements for that of ith compartment? It will be Ni plus Gi minus 1 total number of objects combination number of particles, that number of objects are arranged within that of sample Ni. Okay. So thermodynamic probability of the system W is equal to that product I from 1 to k, expanding that combination, a rule for combination n combination r, that is n factorial divided by r factorial into n minus r factorial, rule of combination. That rule is used Ni plus Gi minus 1 factorial divided by r factorial. So Ni factorial, next n minus r factorial, that is Ni plus Gi minus 1 minus Ni factorial, or W is equal to product I from 1 to k Ni plus Gi minus 1 factorial divided by n factorial Ni plus Gi, here Ni cancel out, that is Gi minus 1 factorial. Look here, Ni and Gi are very large numbers. So Ni plus Gi minus 1 can be neglected as Ni plus Gi, as Ni and Gi are very large numbers, so these are neglecting 1. They neglect 1 means that value will be same if we omit minus 1. Product I from 1 to k Ni plus Gi factorial divided by n ni factorial gi factorial. Okay. Now taking logarithm on both sides, taking logarithm on both sides, so ln w is equal to, that product changes to summation, that is summation over I ln a by b, ln a minus ln b, ln ni plus gi factorial minus ln ni factorial into gi factorial. Or ln w is equal to summation over I ln ni plus gi factorial ln a into ln b, ln a plus ln b minus ln ni factorial plus ln gi factorial. Or ln w is equal to summation over I ln ni plus gi factorial minus ln ni factorial minus ln gi factorial. Ln of that factorial can be expanded by using Stelling's approximation. Using Stelling's approximation, using Stelling's approximation, Stelling's formula ln n factorial as n ln n minus n, that is the formula. Therefore, let it will be equation number 1. Equation 1 written as ln w is equal to summation over I ln ni plus gi factorial. That formula is used, ni plus gi ln ni plus gi minus ni plus gi. Next, ln ni factorial, ni ln ni minus n I. Next, minus ln gi factorial, gi ln gi minus gi. Expanding inside that of brackets, so summation over I ni plus gi ln ni plus gi minus ni minus gi minus ni ln ni plus ni minus gi ln gi plus gi minus ni plus ni minus gi plus gi. cancelled out, we obtain summation over I Ni plus Gi ln Ni plus Gi minus Ni ln Ni minus Gi ln Gi. That for ln W. As we consider in equilibrium state, so the thermodynamic probability will be maximum. If we consider its differentials, so what we obtain? Differentiating both sides with respect to Ni as Gi to be fixed number, and the number of elementary cells which one is fixed, and Ni to be a variable quantity. Differentiate with respect to Ni. So you obtain d of ln W is equal to its differentiation of that term, first term differentiation, second term as constant, second term differentiation, first term as constant. Its differentiation dni constant term ln Ni plus Gi plus differentiation of second, first term as constant Ni plus Gi, which is differentiation ln of that quantity, that is 1 divided by Ni plus Gi into dni, differentiation of Ni. Next term, this is summation over I within that of bracket minus Ni ln Ni, differentiation of first term, second term as constant, so dni second term as constant ln Ni. Next differentiation of second term, first term as constant, so minus Ni 1 by Ni into dni as entire term, Gi to be fixed, so its differentiation will be 0. Ni cancelled out. Differentiation of ln W is equal to summation over I dni ln Ni plus Gi again, that term cancelled out, so plus dni minus ni ln ni minus dni that within that of bracket term plus dni minus dni cancelled out, d ln w is equal to summation over I, that term n dni ln ni plus gi minus dni ln ni. From these two terms dni as common, so d ln w is equal to summation over I ln ni plus gi minus ln ni whole into d ni. Let an equation number 2. Okay, now we use the condition for most probable, or we can say it as the equilibrium state. For most probable or in equilibrium state, the thermodynamic probability W, thermodynamic probability W is maximum, hence d ln W will be 0. Therefore, the summation term, summation over I ln ni plus gi minus ln ni whole into dni is equal to 0. That equation number 3. Here we taken a thermodynamic system. That thermodynamic system is an isolated system, an isolated thermodynamic system. So the total energy within that of system is constant, and number of particles also constant. These two constraints we can use to derive its statistics. Constraint number 1, as the system to be isolated, so total number of particles is constant, that is total number of particles n, which is written as summation over I from 1 to k ni, that is constant. Therefore, d n. dn will be summation over I from 1 to k dni, that constant differentiation results as 0. So that can be written as summation over I dni is equal to 0. Let us write an equation number 4. Similarly, for energy, the total energy also constant, that is total energy U is equal to summation over I from 1 to k. For ith compartment, the energy will be number of particles within that of compartment, and mean energy Ui, that is constant. Therefore, its differentiation du is equal to summation over I from 1 to k, that is Ui dni will be 0. So, summation over I Ui dni is equal to 0. Equation number 5. Now, we can multiply a constant to that of equation number 4, another constant to equation number 5, and subtract these two equations from that of equation number 3. Since dni is independent, now multiplying alpha by equation 4, beta by equation 5, and subtract them from equation number 3, we get the summation over I ln ni plus gi minus ln ni alpha multiplied here minus alpha, beta multiplied here minus beta ui. From all these terms dni is common, is equal to 0. As we say, dni, the variation in dni are independent of each other. So, the entire summation of that of given equation will be equal to 0. So, write ln ni plus gi minus ln ni minus alpha minus beta ui is equal to 0. As I say, dni is independent with each other. The expression ln a minus ln b, so ln a minus b, ni plus gi divided by ni, this constant to another side, so alpha plus beta into ui. ln to this side, so Ni plus Gi divided by Ni is equal to e to the power alpha plus beta ui. Ni by Ni 1 plus Gi by Ni, Gi by Ni is equal to e to the power alpha into e to the power beta ui, or simply Ni can be written as, first one is subtracted and then it will be divided to that of Gi. So Gi divided by the term e to the power alpha into e to the power beta ui minus 1. The constant value beta known to us 1 by kt, so that expression can be written as Ni is equal to Gi divided by e to the power alpha, e to the power in place of beta 1 by kt, it is ui divided by kt minus 1. This one is the expression which is called Bose-Einstein distribution law. Bose-Einstein energy distribution law. For a particular situation, the value of alpha, which is a constant, is to be determined. So here, with the help of this video lecture, we understand the concept of Bose-Einstein's statistics. First, calculating the thermodynamic probability of that of system. Mathematically, we simplify. For the condition for most probable macro state, the differential result will be 0. To another constraints for statistics, for number of particles and energy to be constant, and finally we obtain the expression which is called Bose-Einstein distribution law. So, with this useful and informative notes, let me wind up the session. Thank you.